Okay, pick up here where we left off. So we were looking at the electron transport chain. Can anyone recall some of the steps that happen before we get to this point? So what are the steps or the phases that we discussed on Monday that would have occurred before we get to the electron transport chain? Let's kind of start there. All right, perfect. Thank you. Yes. So glycolysis, the linking step, and then the Krebs cycle. And I'm also seeing glycolysis. So absolutely correct, right? We had glycolysis, which is that first step. This is where we take a molecule of glucose and we begin to oxidize it through a series of enzymatic reactions. All the while we're accumulating electrons, right? And then we're making a small amount of ATP. And then the linking step, so that intermediary step where we go from pyruvate, which is the end product of glycolysis, and we generate acetyl-CoA. We also begin to generate some of the other byproducts, right, such as carbon dioxide, along with more electrons. And then the Krebs cycle was the third or second phase. And this is where we have that cyclical, a series of reactions, and acetyl-CoA is the main substrate as well as the final product. And here we generate more electrons, more ATP, right? One per acetyl-CoA, in other words, one per pyruvate. And then we also will generate, those electrons that will be going to the mitochondria. So those are the things that would have preceded what we're looking at now. And so the importance there is you want to think about the electrons that we were accumulating via the electron carriers, so FAD and NAD. And so those are going to be really important as far as understanding how we generate ATP in the mitochondria. All right. The other thing that we left off saying here is that oxygen must be present for oxidative phosphorylation, and specifically to act as the last electron acceptor. So we talked about this being a chain of passing electrons from one complex to the other. And in order to keep those electrons moving, oxygen has to stand by and accept those electrons at the end in order to keep that chain continually moving. And in doing so, we're creating a gradient, and we'll talk about that will end up making ATP. All right, so let's actually begin there by illustrating that. Okay, so the electron transport chain. Is the actual mechanism. Okay. And then the mode of making ATP is by oxidative phosphorylation. All right. And we want to emphasize here that this requires oxygen. Right? Hence that term oxidative. So let's kind of set the scene of where this takes place. This is taking place in the mitochondria. And we know that the mitochondria are these oval-shaped, double membrane organelles, right? They have an outer and inner membrane. So highly folded cristae inside here. And exactly where this is taking place is across the inner mitochondrial membrane. All right. So we've got the outer membrane, the inner membrane, and this is going to take place right across here. So let's draw a close-up of that location. So we have our outer mitochondrial membrane. Let's start again. We've got our outer mitochondrial membrane. Right, we've got the inner mitochondrial membrane. Okay, and as a result, this space in between is going to be called the intermediary or intermembrane space, excuse me, the intermembrane space. Oops. Let's do that again. So this is the intermembrane space. Okay. And as a result, we're going to have the mitochondrial matrix, which is going to be the innermost, and here is the matrix. So that's going to be this area down here. This would be called our mitochondrial matrix. Let's put it on this side. So the mitochondrial matrix, right? So the first thing we also want to establish here is that within the inner mitochondrial membrane, we have a series of complexes, all right? We've got complex 1, which is inserted in the membrane here. There's no 2, we've got complex 3. And I don't need you guys to memorize the names of these complexes either, but I do want you to know that they are in the inner mitochondrial membrane. All right. And then at the very end, we have a unique complex or carrier, which is called ATP synthase. All right. Okay. So this is ATP synthase. Oh no, sorry. Hang on, guys. I forgot how to reset this. Okay, I apologize. So we've got ATP synthase. Right, we've got our various complexes, complex 1, complex 3, and then complex 4, okay? Now, what has to happen is we're gonna have to be moving electrons across each of these complexes. So that's gonna be the shuttling of electrons coming to the mitochondria, and this is what their role is going to be. So we pass these electrons into complex 1. All right, we're bringing all these electrons here in their reduced form, right? The carriers in their reduced form. So we have NADH plus electrons, and those will be oxidized to NAD plus. In other words, those electrons are going to be liberated and they're going to be passed into complex 1. Okay. So here is oxidation. Same thing with FAD. We have FADH2. We're going to oxidize that back to FAD plus. And then we're going to liberate those electrons and pass them into complex 1. Now, as we pass electrons from complex 1 to complex 2, we're going to actually pump some hydrogen ions into the intermembrane space. So let's talk about the hydrogen ions and their different concentration. So typically, there is a smaller amount of hydrogen ions in the mitochondrial matrix, right? These are our hydrogen ions. And then there are more hydrogen ions, right? A greater concentration of those in the intramembrane space. And the reason for that is because every time we pass electrons from one complex to the other, we pump some of the hydrogen ions through this complex and into the intermembrane space, right? And the reason that we have to use electrons to do that is because this is not passive, this is active transport. To go from a place of low hydrogen concentration to a place of high hydrogen ion concentration, we need energy to move these hydrogen ions to this region, right? And so as an electron goes from complex 1 to complex 2, we move some of these electrons through the complex and into the intermembrane space, all right? And so then we go from here to there, and we pass some hydrogen ions into the intermembrane space. And again, as we pass electrons from here to here, we move these hydrogen ions out into the intermembrane space. Okay, I'm going to pause there and see if everyone is okay with that so far. All right, so just to recap, we have a lower hydrogen ion concentration in the mitochondrial matrix. And so in order to move these hydrogen ions against their natural gradient from a place of low concentration to high concentration, we need the electricity or the energy that is liberated passing these electrons from complex to complex, okay? And that is going to have a role. So we need to have more hydrogen ions here than we do down here so that we can drive ATP synthase, right? The final complex here will move these electrons back down their gradient. So this will be a passive movement from high concentration to low concentration. And in doing so, ATP synthase will take that energy to make ATP. All right, to make ATP. So we're going to generate 34 ATP in this last carrier. Okay, and this is per molecule of glucose. All right, now where these electrons are going to go. So we've talked about electrons going from complex 1 to complex 3 to complex 4. They have to go somewhere, right? There needs to be a method to keep the chain moving. And so this is where oxygen comes in. So oxygen is standing by. All right, so here's oxygen. It's going to accept these electrons. Actually, put this in here, oxygen. It's going to accept these final electrons, and that is what will keep the chain moving in order to move the hydrogen ions into the intramembrane space and then move them down ATP synthase in order to generate ATP. Okay, so in this way, oxygen is acting as the final electron acceptor. Okay. And then just to illustrate what's happening here in terms of ATP synthase, we're basically phosphorylating. So we have 34 ADP plus phosphate. And then by the energy liberated from ATP synthase, we're going to phosphorylate those to generate 34 ATP. Okay. All right. Again, I'm going to pause and see what questions we have on this, and then we'll summarize this again, and then we'll keep going. All right. So the things to take away from this is the electrons that have come from glycolysis, etc. They need to be in the matrix in order to drive the electron transport chain. Okay, so while we think about glycolysis as a separate way to make ATP, it's still contributing, right, indirectly to the electron transport chain and to oxidative phosphorylation. The other thing we want to remember here is that oxygen must be present for this to continue. So in the absence of oxygen, this chain halts. The passing of electron halts, and we stop making ATP. Why do we stop making ATP? Because we stop passing hydrogen ions from the matrix into the intermembrane space, and we stop passing those hydrogen ions passively down ATP synthase, and we stop generating ATP. So oxygen is essential to continue the passing of electrons, and then also indirectly to making that ATP.